Alright, in this video we're going to be going over some of the basic definitions of acids and bases and how they kind of interact with each other. So we'll start off first with some basic properties. So if we talk about acids, some of the basic properties of acids are, well, in general, acids will have a pH of less than 7, right? So lower pH for an acid. They tend to be very corrosive. If you put an acid on a reactive metal, you're actually going to form hydrogen gas. And if you were ever to taste an acid, acids have this very sour, tart type of taste to it. Right, bases on the other hand, right, pH tends to be greater than 7. Now, bases are still extremely corrosive. They just corrode through a different mechanism than acids. So when we're talking about things being corrosive, it's not whether it's acidic or basic, it's how strong the acid or base is. Bases are actually very commonly used. They're cleaning products, right? Most of the detergents and soaps and everything else that you use come from bases. And if you're ever to eat a base, bases taste fairly bitter, right? One of the reasons why dark chocolate tends to have a very bitter taste to it is because it has a lot of basic components in it. So there are 3 different definitions for acid and base that you can look at. One's called the Arrhenius definition, one's called the Bronsted-Lowry definition, and one is called the Lewis definition. We're going to be working with, in this case, right, so our definitions are going to be based on Bronsted-Lowry. And the way that they define an acid is they define an acid based on the proton. Proton is an H+ ion. Acids are anything that donate or give up protons. Right, so the formula for an acid is really easy to tell because all acids will begin with hydrogen as the first element in their formula. Right, so for example, hydrochloric acid, HCl, acetic acid, HC2H3O2. Now the general equation when we put an acid in water, and whenever we use an acid, our generic acid is HA, so hydrogen followed by acid. And the general formula is that HA, when you put it in water, will give up its hydrogen to form A-. Right, so HA will give up its hydrogen atom to form A-. The water takes in that proton to become H3O+. Right, so acids give up hydrogen ions, right? So just individual protons, H+. Now we can further subdivide acids into strong acids and weak acids. A strong acid is when 100% of the HA molecules give up their proton. Right, so all the HA will react to form A-. That means it's strong. For a weak acid, only some of it will. You'll still have some of your original acid remaining. We have 6 strong acids. These are commonly nicknamed the Big Six. We have hydrochloric, hydrobromic, hydroiodic, sulfuric, perchloric, and nitric. Those are the 6 strong acids. Any other acid is by definition weak. Right, so those 6 will break up 100%. So what that means is that HCl will break up 100% into H+ and Cl-, or I could say HCl plus water, 100% H3O+, and Cl-, right? So this is 100% because strong acid. A weak acid, something like, for example, let's say acetic acid, right? Acetic acid is HC2H3O2. If I put that in water, I'm going to form acetate, so that's C2H3O2- and H3O+. This right here is only about 5%, right? So weak acid, this particular weak acid is only about 5%, so it's not a very strong acid. Hydrochloric is 100% of it will react. That's the difference between strong and weak. Doesn't matter the concentration, it just matters how much it will break up. Bases work kind of similarly, right? So if an acid donates, a base accepts. Now, the way that we tell what type of compounds are bases is, first thing is anything that ends in OH, right? So anything that ends with OH at the end of it will be a base. Any negatively charged ion can also be a base. So, for example, if I take the nitrate ion, nitrate is NO3 minus. If it's negatively charged, it can act as a base because I can put hydrogen on front of it and form something else. Some of the other compounds will depend on structure. Usually we cover this after we do molecular structure, so it's a lot easier for me to give explanations. In general, when I'm saying based on structure, a lot of nitrogen compounds tend to be basic, right? So like your amines and that sort of thing, those tend to be basic compounds. But we'll get more into that towards the end of the year. Now, the generic form of a base. So for a base, we're just going to use B when it reacts with water. B plus water. So what's going to happen here? This is our B is our base, which means that water is going to be our acid in this case. This hydrogen is going to travel from water to the base to form Hb plus and hydroxide ions. Under the Arrhenius definition, anything that produces hydroxide is classified as a base. So in a lot of cases, these two definitions will overlap. Water in this case is the acid, B is the base. The base accepts the proton, becomes Hb plus, and again, B is just going to be whatever random base we want it to be. And just like acids, we can have strong and weak bases. Our strong bases are group 1 hydroxides and group 2 hydroxides, right? So for a more exhaustive list, we're talking lithium hydroxide, sodium, potassium, rubidium, cesium, francium. And then our group 2s, we're talking about beryllium, right? And then if I just keep going down, magnesium, strontium, calcium, and barium, they are a little bit out of order. But in general, these are going to be your strong bases. Any other base is going to be weak. Now, the other thing that I need to talk about when I talk about acid-base definitions are what's called a conjugate pair. Here's a reaction. This is an acid-base reaction. We have nitrous acid, HNO2, reacting with ammonia, which is our base, producing nitrite ion and ammonium ion. All right, so if we look at this reaction, I'm actually going to draw out what happens. This hydrogen will travel over here. Right, so HNO2, the H comes over to the nitrogen. That leaves us with NO2 as a product, or NO2 minus as a product, and NH4 plus as the other product. Now what we can do is we can divide this into two relatively related pairs. Right, our first pair is going to be nitrous acid and the nitrite ion. Our second pair is going to be ammonia and ammonium. So these are two pairs. Every acid-base reaction is always going to consist of two pairs, right? So what we know that HNO2 is an acid, right? Because it gives up its hydrogen. If it's giving up the hydrogen here, that means NH3, which is accepting it, has to be our base. Ammonia is usually a base. But let's look at the reverse reaction, because you see this little thing right here, this little arrow in the center. The fact that it goes in both directions means that this is a reversible reaction. So we can look at the other reaction. Now in the other reaction, what's going to happen is that the ammonium is actually going to transfer the hydrogen back. Right, so we have two competing reactions. One where the HNO2 gives up the proton, one where the NH4 gives up the proton. In this case, NH4, since it's giving up, is acting like an acid. NO2 is acting like a base. We have two different reactions here. We have two sets of pairs. These related pairs are what are called conjugates. The only difference is that they differ by exactly one proton, right? So HNO2 and NO2 minus. The only thing that these differ by is an H plus. Same with NH3 and NH4. And looking up here, HNO2 is the acid, NO2 minus is the base. Every pair will have one acid and one base. Just like our other pair here, ammonia is the base, NH4 is the acid. Right, so every reaction will have one acid-base pair. These are conjugates. Or I should say two acid-base pairs that are conjugates of each other. Right, so this is going to be the key thing to pay attention to when you're doing the problems from the book. So we'll actually do an example of a problem in the book. Right, so here's a reaction. In this reaction, we have the acetate ion reacting with HiO3. And again, notice this is a reversible reaction. So I'm going to ask you to identify each of these substances as an acid or base. What are the conjugate pairs? And draw an arrow showing the direction of the proton movement. Well, let's start off by looking at the pairs, right? The pairs are related to each other. They're actually very easy to identify. So our first set of pairs is we have acetate, so C2H3O2 minus, and that's going to be paired with HC2H3O2. Our second pair is going to be HiO3 with IO3 minus. Right, so those are our two pairs. Now to identify them as acids and bases, what we're actually going to do is look at what's happening in the reaction. Okay, so to identify these, I'm going to look at acetate, and I'm going to look at HC2H3O2. In order to get from acetate to HC2H3O2, what has to happen is this thing right here has to pick up a proton, right? So it has to gain a proton to become this thing on the right. So that means that this is going to be a base. Acetate ion is our base, right? So I'm going to label this as base. If this is our base, then we know everything else, right? HiO3 has to be the acid because this has to give up the hydrogen. If C2H3O2 minus accepts, HiO3 has to give up. So that's our acid. And then on the other side, if acetate is our base, HC2H3O2, since it's the conjugate, has to be an acid. Right, I'm actually going to label this as conjugate acid. So here we have our base and our conjugate acid, and HiO3, since that's an acid, IO3 minus has to be the conjugate base, or CB. Right, so that lets us label everything as an acid or a base. And then the last thing we have to do is draw the arrows showing the direction. Well, remember, the hydrogen always goes from acid to base. So my arrow is going to go from the acid to the base, H+. And on the other side, it's going to go from the acid to the base H plus. Right, so that's showing where the proton is moving. So this is basically what I'm going to ask you to do in the questions from the book. All right, if you have any questions, please feel free to email me. Otherwise, I will see you guys after vacation.